Yeah. So now that I have started the recording, so Shanmupriya, please type in your background and I'll share my screen and then I'll show some problems. Yeah. So then we can discuss. Yeah. Can you see my screen, Shanmupriya? Please just unmute yourself and tell me so that I have an idea whether you are able to hear or not. Can you see my screen? Where here you see some problems over here. Can you see my screen, Shanmupriya? I hope you can see. So what I'll do is I'll let you see the problems and I'll wait for some other people to join in the meantime. Maybe I'll wait another 5 minutes, after which I'll start discussing the problems. Shanmupriya, can you please tell me whether you can see my screen? I just want to confirm. All right. Yeah. Okay. And then it would be nice if we can solve the problems on the side. I'll of course be doing it, but then if we can do it on the side, it'll be easier for you as well. So that if you have some doubts, you can ask me anytime. Is it all right? And you can always type in the answers in the chat box if you don't want to talk. All right, I'll get started. Let people come in when they are coming. So it would be nice if you can, answer some of my questions, unmute yourself and answer some of my questions, so that it's little interactive. Otherwise, it'll be little too monotonous. All right. So now, most of the problems that I'm showing here are either from the practice problems or some problems that are related to your assignment problems. So after the discussion, you should be able to solve the assignment problems quite easily. So that's the idea. And if you have any doubts, please interrupt me in between, and then you can ask your questions. And then it would be better if you unmute yourself and stop me instead of typing in the chat box. So because I'm mostly presenting directly from my word file, so it will be easier for me in that way. Okay, so let's get started. So as you can see here, this week most of the lectures were about heat, work done, internal energy of the system, first law of thermodynamics, and so on and so forth. So as you can see here, the first problem is about isothermal expansion of gas at constant pressure. So basically, what we have here is an ideal gas. First, we have an ideal gas, and then there are about 100 liters of ideal gas, and it expands isothermally against a constant pressure of 1 atmosphere. So until its volume becomes doubled. So basically, we need to calculate the work done. So so just a minute. By convention, just a minute. Why is it happening like this? Give me a minute. Yeah. Got it. So by convention, mm, what is the work done on the system? Let's say we have a system of ideal gas. Work work is positive. Work done on the system is positive if it is expansion or compression. Can you tell? And it is negative for which one? The other one, of course. Yeah. Work done is positive for what? Yeah, let me admit somebody. Yeah. We have Shobnapriya here. Okay. So what I'm basically doing is I'm solving some of the problems that are relevant to your assignment problems. So please keep it little interactive so that we can get through this quicker and you can learn things better. All right. Anyway, yeah. So let's get back to the problem. So we have an ideal gas here, 100 liters of ideal gas that's allowed to expand isothermally against a constant pressure of 1 atmosphere, and it becomes double. So basically, we need to find out what the work done is. It's simple actually, but what I want you to tell me is work is positive for expansion or compression of the system, of a gaseous system. Let's say we have a box. Here we have an expansion. If it is compression, then what is the sign of the work? And if it's expansion, what is the sign of the work? Can anybody tell? One of you please tell. Or at least type in the answer into the chat box. Work is positive for compression or expansion. I'll wait for the answer. Work is positive for compression or expansion. Okay. If you guys are not telling, I'll tell it myself. I'll do it myself. Okay. So by convention, so in general, what we do is we have a system and we consider the work done on the system. So basically, when there is compression, work is being done on the system by the external force, whether it's a piston or a mass or whatever we are using. So then work is positive. So it is positive for compression. Okay. And it is negative for expansion because work is done by the system now. All right. So what happens is whatever force we are giving or whatever pressure we are putting, that is not enough. Gas is expanding against it. So basically, it's a negative work that we are doing. So the formula for work done is, by convention, we use this minus P external because it is the, yeah, it is the force or it is the pressure that is given against the system. Then let's say we are putting pressure against the system and then we are compressing it. The delta V is going to be negative, but work has to be positive. So we put a minus sign to compensate that. So now, what do we have in over here? We have delta V is equal to, it's getting doubled, right? So it's double. So the latest volume is the V final volume is minus VI. V initial is 100 liters. We know that. V final, since it's double, is 200. So we have 100 liter. That is the delta V. And we know the pressure is 1 atmosphere. So minus 1 atmosphere. And then delta V is 100 liters. So what we have here is minus 100 liter atmosphere. So that is the work done. So basically this is in negatives. So if you see your example problem, we want it in calories. So that's why we have the conversion factor. 1 liter atmosphere is equal to this much calorie. So we'll just convert it directly. 124.21 calories. So the work done is minus 24. So it is negative because the system is expanding. All right. Yeah. So that's it for the first problem. So now I'll give you a few seconds to ask me any question. I mean, if you have any doubt, you can ask me. Okay. You can just type in the chat box as well. I'll wait. If you have any questions, then we'll continue. I mean, if you don't have any questions, I can go on to the next problem. So the main idea over here is it is a PV work. So the work done should be equal to P into V. So here, constant pressure, volume is changing. So minus P external into delta V. And then work done when it's compressing, it's positive. When the system is expanding, it's negative. So these are the key concepts over here. If you have any doubt, please type or you can ask. Okay, it seems you don't have any doubts. So in that case, I'll move on to the next problem. So you can see that we need volume occupied by 5 moles of an ideal gas at 400 Kelvin temperature and 2 atmosphere pressure. So now, what formula do we use here? Can you tell? Just type in. I mean, you don't have to type in the formula. It's an ideal gas. So what is the equation called? Just type in. What is it called? It's an ideal gas equation. What is it? Ideal gas. Okay, it's called ideal gas equation of state. So we have the ideal gas equation of state, which is the famous equation PV is equal to nRT. PV is equal to nRT. Okay. So now we need the volume. We have to calculate the volume. So we can rewrite the equation as this. So now what and all do we have here? We already have n is equal to 5 moles. N is equal to 5 moles. Then we have temperature is equal to 400 Kelvin. We have pressure is equal to 2 atmosphere. And we have the universal gas constant as well. Okay. So all we have to do is just multiply basic arithmetic. So you can just calculate. I have a calculator. So basically it comes to around 82.06 liters. Zero 06 liters. Okay. This is the final answer. So it's quite straightforward. We have, we can just calculate different properties like pressure, temperature, when all the other, and also number of moles when all the other variables are given. So this is a handy equation that a lot of people use. Okay. Do you have any doubt? If you have any doubt, please type into the chat box or ask. I'll wait for a few seconds. Okay. So, can you tell me what happens? Can you answer the third question B? I mean, leave the A, 3A, but can you answer 3B? Because I mean, there's a qualitative answer there. You can answer it mathematically and qualitatively. So, what happens to the van der Waals equation at high temperature? So, do you know the van der Waals equation? Yes or no? Van der Waals equation of state for a van der Waals gas. If you have, I mean, if you have listened to the lectures, you might know. Did you? Okay. Van der Waals equation of state. We can write it in different ways. I'll follow the convention that is followed in class. It's a plus here. Sorry. Sorry, it's a minus here. Correct. It's a minus. Yeah. Are you aware of the equation? Yes or no? Yes or no? Are you aware of the equation? Type in. I mean, just type in. And also type in what will happen at high temperature. It's a little qualitative. Okay, maybe I'll just little bit explain it. Okay, so this is the Van der Waals equation of state. So this is pretty similar to ideal gas. Okay, so if you see ideal gas, we know it's PV is equal to nRT, or it can also be written as P V bar is equal to RT, where V bar is the volume density. So now we can write this equation in this form as well. So I'll do that. So what I'll do is I'll rewrite it minus this side. I'm taking adding and subtracting a plus. Sorry, I'm just adding a plus a divided by b bar square on both sides. So basically, what will happen is we can like this, and then this b minus b will go to this side is equal to RT. So you see here, it's quite similar. You know, P there is some correction over here. For V there is some correction. So this B is related to the excluded volume of your gas particle, while this A is related to the intermolecular interaction or attraction between the gas particles. So that's what we are. So that's what this equation tells. Okay. So now what we need to do is we need to see how this equation changes at high pressure and at high temperature. So we'll take the high pressure case first. High P. At high P, so pressure is over here, right? So what would happen is at high pressure, okay, this term this term will be much higher than A by V square. So that's what we'll see. Let's just push this down. At at high pressure, what happens is P will be much higher than A by V bar square. So which implies P plus A by V bar square is approximately equal to P. So the equation reduces to something like this by RT. So PV minus PB is equal to RT, and therefore PV bar is equal to RT plus PB. So this is the reduced form at the case of high pressure, where the pressure kind of depends only on the excluded volume and nothing else. Because basically it's quite intuitive, because we have very high pressure that the molecules are getting compressed. So when the so I hope you can see my hand. I'll just little bit go back. So what happens is at high pressure, the molecule basically becomes extremely, they'll come close to each other. So only thing that's keeping them away from each other is the excluded volume, because there is a repulsive term over there, and you can't get past those strong repulsive interactions because of electron club. So that's what is happening at high pressure. Okay. So now I'll go back. So next is what will happen at high temperature. High temperature is quite intuitive, because even in class, sir was mentioning that at high enough temperature, all the particles will have a lot of will have high velocities. Okay, so they have high velocity, and therefore and also high volume, high velocity and high volume. So they'll occupy a very high volume. So that's what would happen here. So if you see here, at high temperature, this volume, this term, so at high temperature, the when temperature increases, volume becomes large. Okay, becomes really large. So A by V bar square will tend to zero, will be very close to zero, and then V bar will be much greater than volume, because this is just the excluded volume. Basically it's like size of the atom. So in that case what will happen is, so this implies P plus A by V bar square is approximately equal to P, and this implies V bar minus B is approximately equal to just V bar. So basically what happens is, in that case, the ideal gas the van der Waals equation becomes an ideal gas equation. It's as simple as that. Ideal gas behavior at very high temperatures. Ideal gas behavior. Because the particles are far apart and they don't see each other, so basically there's no interaction. So if there's no interaction, then this term has no role to play. And then again, if they are not interacting, then there's no point of including the excluded volume effect as well. So that's the idea. All right. So let's see. If do you have any doubts on these concepts? If not, I'll carry forward. Otherwise, we can, I can clear your. If you have any doubts, I can clear it. Then and there. Yeah. I'll wait for a few seconds. Okay, good. Y- You're following till now, right? I mean, if you're able to follow, that's well and good. Yeah. Able to follow, right? Yeah. Okay. Okay. So the next question is again a simple question that's based on the. Oh, sorry. I will have to change this. This is for oxygen. Yeah. So basically, what we want to do is, given A and B in the Van der Waals equation and other conditions, can we get the pressure exerted? Basically, we have the Van der Waals equation of state, which is P is equal to RT by RT by V bar by B minus A by sorry A by V bar square. So we have A and B, those are given here. You see here, A and B are given here, and then we of course know the R value. So I'll write what and all we know here. So we know N, which is 2 moles. We know the volume, which is 1 decimeter cube, which is basically 1 liter. Okay, and then we have the temperature, which is 310 Kelvin, and R value when when it is in terms of liter atmospheres and all, R value is, let me just have a look at it. I think 0.0826. Yeah, 0.0826 liter atmosphere moles per Kelvin. All right, we have this. So basically, we need to calculate the pressure exerted by this gas. So we have V and N. We don't have V bar. So V bar is basically V by N. So we have 1 liter divided by 2 moles is equal to divided by 2 is equal to zero point 0.5 liter per mole. Liter per mole. Okay. So we have this. Now we can just substitute everything in the equation. Always it's a good idea to keep track of the sorry always it's a better idea to keep track of the units as well, so that we don't lose some conversion factors or something like that. 206. So this is in liter atmosphere moles per mole per Kelvin. Again, T is into 310 Kelvin divided by, what do we have here? V, which is 0.5 minus B also has the same unit. So you see liter per mole. So we don't have to worry about units over there. 86 liter per mole. And then we come to the second term here. Now second term, just create more space. Yeah. Second term is on A by V square. So A is 1.363 liter square atmosphere and mole divided by, mole minus 2. Okay. We can just shift this up a little. Sorry about this. Divided by V bar square. So this will be 0.5 squared, which is 0.25, and then liter squared and mole minus 2. So let's first deal with the units. Liter gets cancelled, mole gets cancelled, Kelvin gets cancelled. So we're left with atmosphere, which is a pressure unit. That's good. Again, liter gets cancelled, mole gets cancelled. We are again left with atmosphere, which is the pressure. So that's well and good. Now we can take out our calculator and then just calculate things quickly. Yeah. So we have 0.08206 into 310 divided by, where do I open bracket? Okay. It's not there. Let me shift to side. Yeah. I kind of have to type it. Okay. So 0.08206 into 310 divided by, open bracket, 0.5 minus 0.03186. Okay. And then we have this for the first term, which is approximately 54 point, okay, 54.34. And this is due till 2 decimal points. 34 minus, again, clear, 1.363 divided by 25, which is approximately 5.45. 5.45. So then we have, the pressure, so basically, so now we just need to subtract that. So we have our answer here, which is just 54.34 minus 5.45. Sorry, what am I typing? 3 4 minus. So we have 48.89 atmosphere. So that's quite in the ballpark, okay. But still, you do notice that this is quite a high pressure, right? Because in general, the atmospheric pressure is just 1 atmosphere, but then this one, it's quite high. So that's the kind of pressure that gases can exert just 2 liters of oxygen. Yeah. Okay. Do you have any questions here? Let's come back. Do you have any questions here? You have a similar problem in the assignment. So there, I think it's carbon dioxide gas. Very similar values. I've just changed it to oxygen. So you can do a similar operation for your carbon dioxide gas in your assignment and then go ahead and submit the answers. Okay, if you don't have any doubt, I'll go to the next problem. Okay, so now we have the next problem, which is which is quite easy. This is directly from the first law of thermodynamics. So basically, it's more like conservation of energy or something like this. So what is the formula for internal energy? Can you tell? Can you just type in the chat box? I'll just wait for that. You can just type in just 2 letters. It's okay. U is equal to what plus what? Internal energy U is equal to what plus what? Yeah. Are you sure? I do understand how you are telling that, but a simpler way of putting it out. No, okay. So what you told was not exactly the answer, but we can get what you got actually. But then, so in general, we say internal energy. Energy is equal to heat plus work, right? So, I mean, work, we take it as negative for expansion, and then you take it to this side. I can understand why you put that. So, that's fine. So now delta U is equal to dq. What is happening here? Yeah, dq plus dw or delta q plus delta w or w. Sorry. Yeah, dq plus w So in our system we have constant pressure. Okay, so we have two parts here. Okay, first part is the heat. So you can see here, while undergoing expansion, the gas also absorbs 1013 joules of heat from the surroundings. So basically, system is absorbing heat, so it's going to be, so then Q is going to be 1013 joules. So that is straightforward. So now we need to calculate the second part, which is W. Okay, this is the change in heat, or heat, we can have it like that. Just put it like this. Yeah. So then we have to calculate the work done. So again, there is constant external pressure. There's no changing pressure with volume and all. So this is the heat part. So now we need to get the work part as well. So W, as you know, is minus P external into delta V. So here P external is 1 atmosphere, and delta V, it's going from 30 liters to 10 liters. So that is, sorry, 10 liters to 30 liters. So it's increasing. So it's positive, so 20 liters. So we have minus 20 liter atmosphere, which is equal to, we can just multiply this 20 with 101.3 joules, the conversion factor, and we'll have minus 2026 joules. So this is the work done. So we have the work done as well, which is minus 2026 joules. So the after this, since we got this, now delta U, the change in internal energy of the system, is going to be Q plus W, which is quite straightforward, 13 minus 2026 delta U. So the change in internal energy is simple, minus 1016 joules. That is the change in internal energy. Alright. So basically this system, the system has lost some heat. Alright. Okay, can you tell me something? So here, you know, you have a negative change in internal energy. So that is one thing. And this is an ideal gas. Okay, can you see that? It's an ideal gas. So since it's an ideal gas, what is the internal energy of the system? Whether it is kinetic energy plus potential energy, or it is just kinetic energy, or it's just potential energy. Just type in your answer, KEP or KE plus PE, whatever it is. Ideal gas. So because of that, what is the internal energy of the system? Ideal gas doesn't have interaction between the particles. So what is not going to be there? Kinetic energy or potential energy? I'll wait for your answer. It's so the internal energy is only kinetic energy, right? Yeah, you're right there. So it won't have any potential energy since it's an ideal gas. So now I'll ask the second question. So you can see that delta U is minus, it's negative. Okay. So the internal energy of the system is decreasing, which means the kinetic energy of the system is decreasing. Okay. So, how do you relate kinetic energy and temperature? It's directly proportional or indirectly proportional? Direct, indirect. Just type it. You remember this formula? Half mv square for ideal gas, half mv square is equal to 3 by 2 kBT or 3 by 2 RT. Do you remember that? Can you tell from that how kinetic energy is? What is the proportionality between kinetic energy and temperature of an ideal gas? Direct or indirect? I'm waiting, still waiting. Yeah, okay, good. Right there. So basically, here you can see for ideal gas. Let's write that as well. Let's push it down. Yeah. For ideal gas, Ke of the system. So basically, internal energy U is equal to Ke of the system is equal to 3 by 2 kBT. Okay. Or 3 by 2 RT. I mean, doesn't matter. So important thing is it's directly proportional. So since delta U is less than 0, that means Ke delta Ke is also delta Ke. Okay, I'll put plus Ke. Excuse me. Delta Ke is also negative, which implies that delta T is also going to be negative. So what happens is the system cools, temperature of the system decreases. System temperature. So it decreases. So that's what I was getting to. So- okay. Do you have any doubts here? If you don't have any doubts here, we can go for the next question. Let's see. I'll wait for a few seconds. If you don't have any doubts, or if you have something, you can ask. Okay. All right. So the next question is actually more about derivation. The problem is actually this main derivation is coming later in week 3, but then they have asked some questions related to this, so I thought I'll just do the derivation and help you guys with that. So as you can see here, we have we want to get we want to know the formula, or we want to know the work done on a gas when it is reversible and isothermal conditions. Okay. So what we have here is we know that generally small w dw is equal to minus p external and pv. So this we know because it's going to be pressure work, pressure, and delta W. Okay. So the important thing here is when it is reversible, basically what it means is there is infinitesimal change in the variable. There is infinitesimal change at in V, so that between those 2 points pressure is similar. But then over the PV graph, pressure changes. Okay. So what happens is we need to get the pressure external, which is not constant throughout this change from, let's say, V1 to V. Let's say we'll take it V final and V. Let's say we will see the state. The system goes from V initial to V final. Okay, but the problem is pressure is not constant throughout, because pressure is also going to change. It's only temperature that's kept constant. Okay. So as you know, systems, internal energy kind of depends on n number of particles, volume, temperature, and PT. Here we have isothermal, which is temperature is constant, and then n is constant, but V is not constant, and also pressure is not exactly constant. Since this is constant, pressure and temperature and volume has to change. So important term here is reversible. Okay, if it is an irreversible work, or if it is irreversible, I mean, if it's an irreversible process, we cannot use this concept, because in reversible work we are going to go very slowly, infinitesimal, making infinitesimal steps, so that between adjacent steps the pressure is almost constant, but on the overall process pressure changes. So in that case, what we can do is we can integrate, sorry, so then we can work will be, we can integrate from volume 1 to volume final minus P external dV. Okay, so what is the P external here, which is going to be equal to the pressure of the gas. So that is the main idea in reversible work. The external pressure is going to be is always going to be equal to the pressure of the gas. So therefore we can use this above equation, P V minus B is equal to RT, which implies P is equal to pressure external is equal to RT by V bar minus B. So then we just need to integrate this, which is quite straightforward. So pressure minus RT by V bar minus B dV. So now RT is constant. So since RT is constant, we'll take it out. Minus RT. By V bar minus B dV. Okay, so this differential is just the yeah, it's just going to be natural log. So minus RT natural log of minus B VI by VF ln first is VF minus B minus ln I minus B. Finally, the pressure, the work done is going to be equal to minus RT ln V bar F minus B divided by V bar I minus B. That's it. So this is the final expression that we will get. Okay. Do you understand this part? So let's say, okay, same equation. If it is for ideal gas, in the case of ideal gas, it is similar, right? Because this B is 0 there, and then we'll during derivation we'll have N outside, so it's going to be minus nRT. So this is for ideal gas, Vf by Vi. So this is for ideal gas. Yeah. I hope you got this part. I'll just wait for a few seconds so that if you have some doubt, you can ask. Otherwise, I'll go on to the next part. If you don't have any questions, we can go to the next problem. All right. So now, here it is again a reversible isothermal compression of an ideal gas. So we can use the above equation over there. Okay. So what's the above equation? Work is equal to minus nRT minus nRT ln Bf by I. We can use this formula for this question. So we have N is equal to 2 mole, temperature is equal to 400 Kelvin, R is equal to 0.08206 liter atmosphere mole Kelvin. Okay, so now we have Vf is equal to 30 liters and Vi is equal to 10 liters. So it's quite straightforward, right? It's just direct substitution. So that's simple. Sorry. We have minus 2 into 0.08206. And then we have 400. And then ln 30 by 10, which is just 3. ln 3. Sorry, I messed it up. Final is 10. Sorry, final is 10. And then initial is 30. It's a compression, right? I forgot. So it's going to be 10 by, sorry. It's going to be 10 by 30. So it is minus 800 to 0.08206 ln 1 by 3. So let me use the calculator. So we have minus 800 into 0.08206 and then into, it's a compression, right? So it should be positive. Ah, just a minute. 1 divided by 3 ln of that. Okay, now into 0.0206 into 800, and then negative of this because there's a negative sign over there. So therefore it is 72.12. Yeah. So it is 72 point, oh sorry, 72.12. Yeah, 72.12. And what's the unit now? We had this temperature which will go, so it is going to be liter atmosphere. We can always convert it to, joules. The conversion factor was 101.3 joules liter atmosphere. So okay, let me use the calculator. We have this. Let me convert it to this one. Yeah, 101.3. Ha! So it is 7305 joules, which is equal to 7.31 kilojoules, something like that. Sorry, 30 kilojoules. Yeah, 30 kilojoules. So that's the work done. Since it's in compression, you can see that it's a positive work. Okay. Yeah. Now we can go to this problem. Do you have any doubt here? I'll wait for a few seconds. Okay, if you don't have any doubt, we can go ahead. This is the last question. And this question, I mean, this question will help you to answer one of the question where you have certain concepts related to Boyle's temperature. So you can see here, we're talking about something called Boyle's temperature for oxygen gas. So first thing is we know that virial equation, tells that Z is equal to, basically Z is PV by nRT, right? PV by RT. No? Okay. Yeah. Okay. So this tells that we can write we can write any equation of state, or for the gas we can write it in terms of some virial coefficients by V plus C by V bar. Okay. V bar square, so on and so forth. Higher order terms. So now this is called the second virial coefficient. Second virial coefficient, and this is third virial coefficient, and you'll have things like that. So now we also know that Van der Waals equation of state, something like this. P is equal to RT by V bar minus B minus A by V bar square. So in class are taught that we can rewrite this Van der Waals equation of state in terms of Z. And if we do that, we on rearranging, I'll leave that, we get the B, which is the second virial coefficient, as something like this: B minus A by RT. So this is the second virial coefficient. Okay. That's good. Okay. So this is the second virial coefficient in terms of the Van der Waals equation of state parameters. So now this is important because there's something called Boyle's temperature. Okay. So Boyle's temperature is the temperature at which they call it TB. At that point, B is equal to second virial coefficient is 0. So you can see here, if this second term becomes 0, you have the higher order terms. Okay. So this higher order terms will take some time to come into play because it has squared, and this is the main dominating factor over here. So since this becomes 0, for a range of pressure, for a high range of pressure, the Z is going to be 1, and it will act more or less like an ideal gas at this temperature. So now we can, from this equation, we can get the TB. So since B is equal to 0, B minus A by RT B is equal to 0. So then on rearranging, we'll get something like this: B is equal to A by RTB. Yeah. So we have TB, Boyle's temperature, is equal to A by BR. So this is our equation. So now we need to calculate the Boyle's temperature for oxygen gas, where A and B are given. Okay. So this is give me a minute. Yeah. Come on. Next page. Yeah. Okay. So now we need to just calculate the TB, which is here. I'll just see the A value. A value is 1.363 liter square atmosphere moles per square, and this is 0.31. Okay, let me just copy this. I'll paste it there so that it's easy for us. Okay, so TB is equal to 1 by 1.363 liter square atmosphere mole minus 2. And then we have B, which is 0.03186, which is liter dot mole per minus 1. And then we have R, which is 0.08206 liter atmosphere per mole per Kelvin. So I'll just cancel these. Again, liter will get cancelled. Atmosphere and atmosphere will get cancelled. So it's just going to be k inverse in the denominator. So 363 divided by 0.0316 into 0.8206 minus 1. So let's just subtract. Let's just do this calculation. It's quite simple. 1 point, sorry, 1.363 into, sorry, divided by 0.0386. Again, divide that by 0.8216. So which is equal to 521 Kelvin, approximately. Yeah. So that's the Boyle's temperature for oxygen gas. All right. Space. Yeah. I hope you followed this. Now let me see if you have any doubts. Do you have any doubts for this question, or in total all the discussion, or any of the subject matter related to this week's presentation? Okay. If you don't have any doubts, I mean that's it from my side. You're free to go. I'll just wait for a few minutes to see if someone else is coming. Otherwise, that's it today. No more discussions. Okay. Don't think anybody else will come now. I'll stop presentation if you don't. Yeah. So since you don't have any doubts, that's it from my side. You're free to go. Yeah. You can leave. Yeah. Thank you. Thank you for joining.